Bruce is going to tell us about circular encryption.
Okay, so yeah, the things that I'll be talking about are symbolic versus computational security. And one issue that comes up in this setting that I'm going to look at in more detail is this issue of circular encryptions. So in general, when I say circular encryptions, I mean a situation where you have an encryption function and say it could be public key or secret key, but you have this situation where you're using your encryption function in some way to encrypt one of your keys. And we'll see what happens in that situation, how it's dealt with, how we could deal with it in the symbolic setting and also in the computational setting. So to start off, we're just trying to understand something that we could write like this. And our intuition when we write an expression like this is that this represents the encryption of some kind of expression or data under a key K. Now, as far as security, how might we deal with this? So in the symbolic setting, we sort of treat this as some kind of atomic operation. And our way of thinking about that is that really, when we encrypt an expression under a key K, it basically erases all the information that's present in this expression.
So
And
just to make sure with notation, E is the data or E is the encryption function?
oh, no, E is the data. E is the data. So this, yeah, this expression means encryption.
Because of the letter E.
Yeah. But we use E for expression here.
It's
Yeah.
the expression
Yeah.
and the curly brackets are the encryption.
Yeah. Okay, and so in the computational setting, when we think about encryption, we think of having some kind of secure encryption function. So, for example, or chosen plaintext attacks secure encryption of an expression under a key, or of some data under the key. Exactly, yes. Or some more long chain of, of expressions that lead us to some kind of cycle. But before we get to that, just in this setting, there over since the early 1980s, these two sorts of approaches have developed. I think for most of us who do more kinds of complexity theory, the computational approach is probably the more familiar one, but there is a whole body of work where people want to reason about encryption symbolically. So the symbolic approach really started with the work of Dolev and Yao in '83, and then the computational Yes, what became called ping pong protocols. Computational approach, well, Yao was involved there again in '82, and then Goldwasser and Macaulay gave definitions of secure encryption. And so if we told a standard kind of story, then these two views diverged. But there was always some desire to say, if we're reasoning in the symbolic setting, which has certain advantages, for example, if we wanted to do automated proofs, reasoning symbolically has certain advantages. But then because we know the power and the applicability of the computational approach, we'd want to make sure that when we reason symbolically, it actually means something computationally. So this gives us the idea of computational soundness. And the idea that, just informally, the idea is that that security in the symbolic setting should imply security in the computational setting. And the first real result in this direction was given by Mohammad Hajiabadi and Phil Rogaway in, I think, in 2000. And what do they show? I'm still being pretty informal at this point, but they show something like this. In the symbolic setting, they have a notion of what it means for two expressions that may involve sub-expressions with these kinds of encryptions to be equivalent. And equivalence here means something like this. When we treat encryptions as an operation which basically erases the data that appears inside, that once you do that operation and you look at what the resulting patterns that you get, the two patterns are identical, maybe up to renaming of keys, right? The actual names of keys don't matter, but when you erase everything that's appearing under an encryption, what you get are two expressions that look exactly the same in their structure. So what they show is that in that case, if you're able to prove an equivalence like that, then in the computational setting, the computational interpretation of these two expressions are computationally indistinguishable. So these are expressions. This is symbolic equivalence. These brackets mean the interpretation, computational interpretation. And this means indistinguishability. All right, so what do we mean by the computational interpretation? These expressions are just formal symbolic expressions, and they involve these encryption expressions, but we have a way of mapping them to bit strings, right? So we have a way of mapping them to bit strings where expressions of this sort are mapped using a secure encryption function, right? So if we use a secure encryption function as part of our semantic mapping, and we're able to symbolically show that two expressions are equivalent, then this computational soundness result allows us to conclude that the two expressions, their interpretations are computationally indistinguishable.
So can you give a non-trivial example of this implication? What would be 1 and 2 be?
Sure. Well, these expressions are, I'm going to leave something a little bit abstract here, but I'll just use something like this. And let me here, instead of writing E, we'll just suppose that we have atomic data expressions inside of these encryptions for now. So why are these two expressions equivalent? Well, if you see what happens here, first of all, well, let me just do this in real time. First of all, these expressions would just have their atomic data erased, as with this, because they're appearing inside of encryptions. And now, going one step further here, all of this just gets erased by something saying it's just opaque. And so in the symbolic setting, these two expressions are equivalent. And unfortunately, I erased what was in there. But we could go through some reasoning to show that because of the security of encryption, what it really means is that what appears inside. Well, actually, what I said isn't quite true there. Unfortunately, in some settings, it depends how we're treating this. But certainly, the length of what was inside here was different from the length of what was inside here. And we know that although secure encryption hides all the content of a message, it doesn't hide the length of a message. So I really should have had two messages inside of here. And then if we had, if the insides had the same length, then it would be clear why the resulting interpretations are computationally indistinguishable.
So you're assuming something like that, okay?
I am, yeah. Now, it turns out that a body, yes?
In that example, why did you move the first step? I mean, couldn't you just go the...
Oh, I could have gone from the outside instead of from the inside. Yeah, certainly, certainly. Okay. We're getting to that. But for Abadi and Rogaway, they actually didn't use standard notions of encryption. So they had an encryption, they thought of encryption functions which hide the length of the input. And so in their setting, this wouldn't happen. But in later settings and what we're going to consider, the length of the message actually does come into it. Okay, so yeah, so what happens in the Abadi and Rogaway setting is that this soundness theorem is true, but if we have, say, a subexpression of a key encrypted under itself, or some longer chain which gives us a circular encryption, then their soundness theorem is not going to hold. And because in their approach, certainly when you have our rule which says that if you have an encryption, you basically just erase what's on the inside. So here, encrypting this key under itself, the key just disappears on the inside, but so in the Abadi-Rogaway setting, the encryption of a key under itself is secure, but it was known back to the time when Goldwasser and Macaulay first introduced secure notions of a secure encryption computationally, that the kind of security they were talking about does not allow us to encrypt a key under itself. So if we start with E, which is a secure encryption function, and now let's just suppose that the set of keys and the set of ciphertexts is disjoint. Ciphertexts are the possible outputs of the encryption function. then now we'll define E prime. So the encryption of a message M under a key K, well, if it happens that M is equal to K, then we're just going to spill the whole answer and output K. And in any other case, we'll just use our secure encryption function. So at least when it comes to encrypting a key under itself, it's easy to see that you could have an encryption function which is secure if we just use it to encrypt messages, plain messages. But if we use it to encrypt keys, then it basically reveals all the possible information. Yep.
What happens if you're encrypting, say, k plus 1, some function of the...
OK, well, I'll try to get to that later on. I'm not going to answer that right now, but that is an issue. Yeah, we want to think about, actually, so in general, it's not known if, well, what we'll show later on is that based on certain kinds of computational assumptions, we can get encryption schemes that allow various kinds of encryption of the key material, of various functions of the key material. So, but the general issue of whether or not an arbitrary encryption function, which is, say, CPA secure, is also circular secure. Well, we now have results showing that in general that's not the case.
So in general, like there when you were doing that deduction,
Mm-hmm.
K1, K2, the keys inside, they need to be somewhat independent of K3, right? I mean, how is
Right.
the notion of independence incorporated in this thing?
Well, OK, the way it works is that you could just have a directed graph of one key encrypting another key, right? So an encrypts graph, and then you could think of any cycle or clique in the graph. You know, you could think of various structures in the graph which you wouldn't want to allow as legitimate forms of encryption.
Okay, maybe I'm not
Yep.
getting this thing very clearly, but suppose you use the same key, say instead of K3 inside, if K1 was related to K3, suppose it was just the negation of K3, every bit was like K1 was just.
OK, well, in the symbolic setting, that doesn't really mean anything, right? So, all right. So we could have a setting where we think of encrypting individual bits of the key, right? And there are results, positive and negative results about what is possible in the computational setting. Yeah, I'm assuming that the keys are generic. So when we look at the interpretation of an expression, the first thing we do is for any key symbol appearing in the expression, we just assign a randomly independent random string. Yeah, OK.
So what goes wrong there? I mean, in the theorem they proved, what did they assume about the structure of E1 and E2?
They assume that if you have this directed graph, encrypts graph, so they assume that if that graph doesn't have any cycles, then they can do their soundness proof.
But if I'm using K1 squared, or you're not allowed to...
No. You're not allowed to do any kind of arithmetic. Yeah, it's the kinds of expressions we can do are very simple. So maybe I should get to what the language is so that we can get a better understanding of what we're talking about in the symbolic setting. But given the situation where the symbolic setting does not correspond to the computational setting, in the situation where you have key cycles, there's sort of two approaches we could think of. We could weaken symbolic equivalence so that you don't get symbolic equivalence in the presence of key cycles, or we could strengthen the notion of encryption so that we could try to develop encryption functions that do support some form of circular encryption. So the first thing I'm going to do is to look on the symbolic side, a way of weakening symbolic equivalence so that we can get a soundness theorem even in situations where we have key cycles. So this is work by Daniele Micciancio. All right, now we're using this technical term co-inductive. It'll become clear later on what co-inductive means in this setting, but let's just get right into what we're dealing with now in terms of what symbolic expressions look like. All right, so we start off with two sets of atomic data, or two atomic sets, the set of keys and the set of data elements. And so you can see the kinds of expressions that we're allowing here are quite limited. You know, an expression is either just a piece of atomic data, it's a key, and then the only kind of operation we have for building up more complex expressions is pairing. And then, of course, we can have the encryption of an expression under a key. So now, of course, when we're in this formal setting, you know, we're going to have these inductive definitions and then a more and more inductive definitions. So sometimes I'm just going to skip the definitions and just use an example, and hopefully from the example it'll be clear what I'm talking about. But so in what sense?
Because it uses, I mean, there is a computation you are trying to emulate, and it says arithmetic operation, so it uses more than
oh,
like the Yao construction of previous functional evaluation.
certainly, yeah. This is a model where the kind of security we're thinking about is just like a passive eavesdropping adversary that's trying to distinguish two messages or a collection of messages. So certainly, you know, we want to sort of do this kind of computational soundness in the setting of protocols, and that's the kind of work that I've been doing lately, and maybe if there's time, I'll try to say something about that. But I just want to develop some of the background at this point. So so this is an example of an expression in this language. Now we also have something that we call patterns. Yep.
In the line before that, what does the pair of expressions there mean? Don't you have data here, and then you have x to x?
I'm saying that this is just like a BNF definition of what possible expressions are. So I'm saying that if you have any two expressions, you can form a new expression by pairing those two, just forming, you know, an expression consisting of the pair of those two expressions. Yeah, concatenation. Well, so one thing that I do is that I keep dropping off parentheses. So if we were really following the grammar exactly, this expression is formed by, here we have a data element, here we have a key element. Then we can form new expressions by encrypting those expressions. Then we can take a pair of expressions. Then again, we can form a more complex expression by encrypting it. So we also have this idea of patterns, and patterns are just the set of expressions we get when we slightly expand the set of keys and the set of data. So we're going to introduce two new symbols, a little circle and a little box. A little circle represents symbolically what happens when we encrypt a key. So we're saying that, well, what was in there was a key, but now it's been erased because we encrypted it. And the box means what happens if we take some data and we encrypt it. Yeah. Yes. So from this, no. Let me just give a general example of a pattern. I mean, I'll talk later on about how we go from expressions to patterns, but just defining the set of patterns, an example of a pattern would be something like this. And in the case where a circle might appear as an encryption key, we just drop it off. So we don't even bother to write it. Well, it's an example. Yeah, this is an example of a pattern because it's anything that we get as an expression, but we're allowed to now use these new symbols of the circle and the box. So from now on, when I write E, although E generally means expression, it's going to mean any pattern. OK, so what is the relationship between patterns and keys and expressions? All right, so we'll have this pattern function where here E can be a pattern, and T is a set of keys. And what this is meant to represent is what E looks like if we have knowledge of the keys that are in the set T. So this one I have to write out the full definition. The pattern of atomic data is just the atomic data. The pattern of a key that's just appearing plainly is the key itself. The pattern of a pair is the pair of the patterns. And then the interesting case is when we have an encryption. All right, so now the issue is whether or not the key K appears in the set T. All right, so, oh, sorry. If K appears in T, then what we're going to do is just recursively go inside the encryption and take the pattern of what's in there with respect to T. Now, on the other hand, if K does not appear in T, now we're in the situation where we're erasing what's inside of the encryption. Now, I have to define what the structure of an expression is, but the idea is that it's sort of like wiping it out, as I was saying, but we want to have this length-preserving property, so we really want to remember the structure of what's inside the encryption. So the structure will remain, which is basically the length information, but all the actual elements will be erased. Yeah, the structure will have, yeah.
So
Yeah.
you just want to be able to distinguish the, when did you encrypt the key and when did you encrypt
Yes. But I mean, there could be more complex structures inside there as well. Like if you encrypted a pair, it'll record that information as well. Yeah.
I can't understand why this pattern of D, comma T is D length. I'm not sure I get the semantics.
Well, so if we have an expression D that's just appearing in the clear, then we're going to see it. It doesn't matter what keys we know or don't know, because there's no encryption taking place here, right? We've just got D appearing out in the open, so its pattern is unchanged. All right, so then basically the structure of an expression is what we get by just erasing all of the actual content and just leaving the structure behind. And in this case, right, you might think there should be a circle here, but as I said, we're not writing the circle when it appears as an encryption key. Now, all of this that we're doing here is on the way to being able to define this notion of symbolic equivalence. So the next step we take here is, so here we've defined the pattern of an expression with respect to a set of keys. So roughly the next steps, the first thing we want to do is to just look at an expression and say, what's the pattern of this expression when we say, well, we'll look at the expression. Somehow, just by looking at this expression, we're already going to know some keys, and we call those the recoverable keys. And then we think of the pattern of the expression under the set of recoverable keys. Well, okay, that's the whole crux of the matter, right? How do we decide what are the keys that an adversary can recover just by looking at an expression?
So there will be keys that will be maybe in the system shared by legitimate users and like the private key and
Sure, yeah. He'll have some knowledge. and then sort of there's some way once the adversary has this knowledge, maybe that gives knowledge of more keys and so on. But it's the exact way in which we define the keys that the adversary knows that's going to decide whether or not we can do this kind of soundness result with key cycles and without key cycles. All right, so this isn't quite a definition yet because what we're thinking of is for any expression E, this somehow gives us a set of recoverable keys. And then if we take the pattern of the expression under the set of recoverable keys, that's what we're going to call the pattern of the expression. And then symbolically, the two expressions are equivalent if their patterns are identical up to renaming of keys. So we're close to getting to this, but the real issue here is how do we define the set of recoverable keys? So let's look at the Abadi and Rogaway approach first. Okay, so they're going to define this derivation relation. So it's going to be a relation that satisfies certain axioms, and then they'll take the least relation that satisfies those axioms. Ah, yes. So basically, what does this say in terms of key recovery? It says basically start off, since it's the smallest relation satisfying these axioms, we basically start off assuming that the adversary doesn't know anything. Then, well, how could we ever get some key? Well, if some key appears in the clear, then the adversary is going to know it. And then knowing that, yeah, not as the encryption, not inside an encryption. Yeah. So, right. So, and then even in more complex expressions, if something appears in the clear, then we're going to get to it. Now, if there's an encryption, the only way that we get inside the encryption is if we've already been able to recover the encryption key. And so you can see that with their definition, it shouldn't.
If it doesn't, then this relation is empty. T would be empty.
Well, that's certainly true. Right,
try
right.
to think of a situation
No,
where
no, okay. I mean, you would have to assume a situation where there's a flaw in some protocol that allows
No, man, that's not
an adversary to recover a key.
It's not like it's military, it's your knowledge. So if you have some keys and the other guy has some keys and you're exchanging information and some of it you will be able to decrypt and some you shouldn't be able to decrypt.
That's true. You could have, you know, a party who's masquerading as an honest party who, you know, gets access to some key and then uses that to decrypt other messages.
So how was this? I mean, so far you didn't separate different users. You just defined it.
Right, because I'm just.
It's not a view of particular users. It's universal. Right?
It's true. It's just a definition of encryption security. So.
So you can say that the view is the messages that everybody sees and the keys that you have. This is your view.
No, there's no view here in this definition.
No, there's no view. I mean, you have to, but this, the sole purpose of this is really to get a symbolic notion which corresponds to the notion of computational indistinguishability of the interpretations. So you can, on top of that, say, well, maybe in this setting we could apply it because the adversary has a priori knowledge, but within the model itself, it's not doing anything like that. It's just saying, well, the only way that the adversary could get a start would be by having some key appearing in the clear. But anyway, if we had this definition, then it's clear that right, so that a circular encryption does erase the information because of this clause. We'd never be able to apply this clause because we don't know what K is. Or even more. Well, so the adversary gets to see this expression. Now, if we just are applying these clauses here.
These are not the definitions of pattern. These are recoverable or devices.
Yeah, if we're using this definition of recoverable, then this is the pattern.
What are the recoverable sets in this expression?
Recoverable would just be the empty set. Yeah. Well, we start off.
Because there is nothing in the clear.
Yeah, because there's nothing in the clear. Yeah.
And for pattern, did you say you don't keep the bottom case in the pattern? So that in a pattern you just keep certain that are not in subscript.
No. When I'm looking at the structure, when I take the structure, I would erase keys appearing in the as encryption keys. But basically, what we get to is this, right? We have an encryption. We're taking the pattern of an encryption where the encryption key doesn't appear in T. T is the set of recoverable keys here, and so we get this. Now, this is where inductive and co-inductive, those terms come into things, because this is essentially an inductive definition, right? Because we start with the empty set of keys, and then we apply these rules to get the smallest set possible of keys that satisfy those axioms. All right, so now we're going to move on to a different setting where essentially we're going to define the set of recoverable keys in a co-inductive way. And let me just say that really what I'm doing here now is just a very general approach, which would encompass both the inductive and co-inductive approach, but our goal here is now to get to a different way of defining the recoverable keys. So we need some more, to introduce some more terminology. So when we write keys of E, we just mean a key that appears anywhere in E, inside an encryption, in the clear as an encryption key, any key that occurs anywhere in this expression. And when I write parts of E, I just mean all of the sub-expressions of E. So I don't know, is that clear? Do I need to put up some examples or?
Sub-expression is going back in the definition of expression. So everything.
Yeah, right, sure. Yeah. Yeah, yeah. And then we define this set R of E, which are just the keys occurring in E that don't occur just as an encryption key. So they either appear inside, they appear as data essentially somewhere in the expression. So here I'll give an example.
Coming in the clear or?
No, they could be inside, just that they appear as part of a message, and they don't just appear as the encryption key for some encryption. All right, so if we have this expression, K4, K3, and K2 all appear just as, or let's do this to make it clear. So K2 and K3 only appear as encryption keys. K1 appears as an encryption key, but it also appears inside of a message. So when we say the keys that can be, R is kind of recovered under any circumstances, not worrying about adversarial knowledge or something, just the keys that are appearing there as part of a message. Oh, this is a set, yes. I mean, you know, if I was going to like be more formal, I'd make these curly braces be double curly braces or something. But yeah, this is just the set K1. All right, so basically, a lot of what we are going to do now is the result of these three equations that I can write down. So this is relating the pattern function, or just about the pattern function in the first two cases, and then a relationship between this R function and the pattern function. And these are all pretty obvious, so I'm not going to prove them. But the first one's obvious, that if you have the set of all keys, then the pattern of E is just E itself. Here you basically have this kind of composition of pattern function giving you the intersection of the key sets. And here you have this kind of monotonicity that certainly if you take the pattern of an expression and look at the keys that appear there, that's going to be no larger than the set of keys that appear if you haven't taken the pattern. All right, well, let me do another couple of minutes and then we'll take a break. So now, you know, I'm going to do something more general than this Abadi-Rogowe approach. So for any expression, we're going to define an associated key recovery function that we'll call f sub e. And this is an operator on the power set of the set of keys. So if T is any set of keys, the key recovery with respect to that set of keys and the expression E is just what you get if you take the pattern of E with respect to T and then you look at, apply the R function. So, and a very important fact about this key recovery function is that it's monotone. And this isn't hard to show. I'll leave it as an exercise for you to show this just using these three properties of R and P. We can show that the key recovery operator is monotone. And, well, why is that nice?
So is P on the board, but you're erasing the same as P on that other?
Yes, yes, yes. I hope you wrote it down. Well, since it's a monotone operator, we know that any monotone inductive operator has both a least fixed point and a greatest fixed point. I think that's a result of Tarski. And so we're going to define these fixed points. We'll write little fix of Fe for the least fixed point. And one way of thinking about the least fixed point is just to start off with the empty set and then repeatedly applying Fe until we get to a fixed point. And then the greatest fixed point we can think of as what we get if we start off with the whole set of keys and repeatedly apply the key recovery operator and take the intersection of all of those. And so now, essentially what we have is, well, we already had little pattern of E, which is just that's the Abadi-Rogowe notion of pattern. But now we also have Daniele's, Micciancio's notion of pattern, which is what we get from the greatest fixed point. Okay, so what I want to do, let's take a 10-minute break or so, and then when we come back, I'll try to show you that if we use this notion of pattern, we'll get a soundness theorem which holds even in the presence of key cycles. With respect to this notion, we'll get a soundness theorem. This one this is the Abadi-Rogueway notion. I mean, it looks slightly different, but you can basically see that this key recovery operator here is just the least fixed point of the F sub E. Yeah. All right. Oh, you're early?
Well, I am, but that's big.
Well, what's the confusion?
It was way back.
Oh.
I did it with the boxes and the dots.
The box is like represents some encrypted data, and a circle represents.
Why did you have to introduce the boxes and the dots?
Well, because we
Was it
eventually
just a
want to say.
shorthand, or was it something else?
No, that's of a pattern. Yeah, right. See, because the equivalence between expressions is if their patterns are identical. So you'd actually need to have, these patterns, and you look at the patterns and say, if those patterns are identical, then the expressions are equivalent. Well, the smallest fixed point's pretty easy, right? Because it says you start off. So you've got this.
So R is like all of the keys I could get if I knew that set T and I were looking at everything that appeared in this expression, or R of P.
Right. R, yeah.
This key recovery function.
Right. It's saying. So yeah, you start off with with a set of keys. You look at you then erase everything in the expression that you can't see if you only know those keys, and then you say, well, after that, now what keys are left?
And then if I start out knowing nothing,
Yeah.
then what can I learn from the expression?
Right.
The biggest fixed point is
I start off knowing everything, then.
then I start taking intersections.
Oh, that helps a lot.
Well, I mean, because, okay. Well, maybe I'll do an example when we start up again. Let me just give a couple of examples of what would happen or what the difference is between the least fixed point and the greatest fixed point. So in this first example, suppose we're looking at the least fixed point. So we would start off at the first step with the empty set of keys. And now if we look at this, if we take the pattern of this expression with respect to the empty set of keys, it basically means that K1 and K2 don't appear. And then when we apply the R function, we just we get back the empty set. And so the key recovery operator bottoms out, or you know, we don't have to go any further. We've reached a fixed point in this case. On the other hand, if we start off with the full, I mean, and when I say the set of keys, of course, we only ever have to worry about the keys that appear in the expression. So if we start off with all keys, and we look at the pattern of this expression, we get back the expression, right? And so then in step 2, when we take the keys that appear as part of a message, we get K1 and K2. And so here we again reach a fixed point very quickly, except that in this case, the fixed point is telling us that this expression reveals all the information about the keys inside of it, whereas in the least fixed point, we got no information. So you can see, at least from this example, why you know, in the Abadi-Rogaway model, you would get this being equivalent, basically, to the encryptions of anything here. In the co-inductive model, this kind of encryption isn't secure at all. So you might wonder, you know, when you start off with all keys, you know, how is it that you ever lose keys, right? So I'm not going to do a least fixed point example for this one, but I'll do the greatest fixed point example. So say we start off with this full set of keys, then what do we have as what we can recover in the next step? Well, all right, well, this we're going to be able to see, right? And of course, this one's just appearing in the clear, so we see it. And then we see K4. But K3 never appears as part of a message. So K3 gets lost in this step. Right? Now, if we take another step here, what happens is that, let me just make sure that I do this right. You lose K4, right. You lose K4 because K4 appears here encrypted under K3. K3 is not in our set. So, and then at this point, we're just going to reach the fixed point, because if we know K1 and K2, well, we always can get K1, and knowing K1, we get K2 here. And so we reach a fixed point. So one thing that's interesting here is that, you know, even though it looks like we kind of have a key cycle here, because K4 is appearing in an encryption under K4, this kind of cycle is okay because there's this intervening encryption by K3, which basically erases the information about K4 inside, so that outer encryption by K4 doesn't really matter.
What is the intuition for the big fixed point? Intuitively, if you gave me all the keys, I will figure out everything you said. Right? Just in terms of actual attack on a crypto system. If I knew all the keys, I knew which keys you use to encrypt various parts,
Well, all right. So we started off knowing K3, but that didn't help us to be able to recover K4 because of the fact that, well, why is that? How can I say that intuitively?
I mean, you can say that the least fixed point is like a proof system where you prove that you know something, and the greatest fixed point is like you prove that something is your own something. You know, well, you do know them, but you don't cause a problem. So like K3 doesn't cause a problem because you never encrypt it, and then K4 doesn't cause a problem because K3 hides it.
Right. So
So a simplest, maybe a simpler example would be just this K4 is encrypted by K3, which is then again encrypted by K4, and that's all. So the point is that if I know all of them, I will not know any of them.
well, I mean,
I don't need to recover K4 inside the, which was encrypted there because I know.
but it's not about what you know, it's about what the expression reveals to you, given that what you can infer from the expression under that knowledge.
Yeah, but I mean, you don't need to infer things you know.
Uh,
I mean, I'm thinking practically, right? I mean, if I knew K1, K2, K3, K4, I know them.
Yeah, but you can take the complement of everything, and then you will see a growing set that you keep adding things that are okay.
No, I understand this. I mean, I
What do you
understand
use it
because I'm asking
What
what's
do
the
you use it
practical meaning of this. I understand it as a formal, completely understand the proof system, as you called it, that's perfectly understandable. But the question is whether this notion of knowledge.
well, okay, maybe it's not good to call it a notion.
Doesn't conform with my understanding of knowledge, because knowledge you don't erase. So if you knew K4.
So a way of thinking about it is like with the inductive definition, it's saying what does the expression reveal, right? Whereas with the co-inductive definition, it says what does the expression hide.
No, I understand the difference.
So it's not no, but it's saying what does the expression hide. So it's saying like we can start off by assuming that it doesn't hide anything, but then we can see that, well, it does hide this particular key. And so then given that it hides this particular key, it also hides this other key.
I understand, but to my intuition, it doesn't hide it at all if I was given.
Well, no, if you knew it, but it's just saying, let's start off assuming that it doesn't hide anything, and then see, okay.
Good.
So this is like a relaxation of all that I possibly know.
Yeah, or it's sort of like, can you think about it in terms of possible knowledge?
No,
I mean,
in the sense that maybe even if this by this recursive definition, even if I get K1 and K2, it's not necessarily that in a practical situation I will be able to get K1 and K2 fully, but certainly I won't get anything more than K1 and K2.
yeah, I think that's a reasonable way of stating it too. Yeah. Okay, so now, of course, once we have this notion of pattern, we have a corresponding notion of equivalence. And so, again, up to renaming of keys. If they're symbolically equivalent, we get the soundness. And I don't think that I'm going to go through the whole proof of the soundness theorem. It basically relies on the following. that the interpretation of E is going to be indistinguishable from the interpretation of the pattern of E under the keys that appear in E. And so really to understand this, we have to dig a little bit more deeply into what the semantic operator is. And so how far do I want to go with this? Basically, the idea is that data elements, keys are going to be assigned to random strings. Data elements are going to be assigned to strings over some fixed set. And the data elements can be fixed, assigned deterministically. So the idea is that we have this assignment, interpretation of keys that we get by just choosing strings independently at random, assigning them to keys. And so then for each key symbol, we have a corresponding key. And then we have an encryption function, a secure encryption function. And the interpretation of an encryption then is what we do is we take the interpretation, and of course, this is with respect to this key assignment. We take the interpretation of the inside, and then we encrypt it. And what's really important is what is the interpretation of let's say if we had the encryption of a structure, when we think of a structure, basically we want to define things in such a way that structure preserves the length of expressions, so that any two expressions with the same structure, when we map them to a bit string, they have the same length. And so then when we encrypt a structure, we can think of that as just taking a string of zeros. We take the interpretation of the expression, take a string of zeros of that length, and encrypt that string.
So in your, in this language, for example, if we do what the example before, K4 encrypted by K3 again encrypted by K4, this one expression, and the other expression is you have some data element or K1 encrypted by K3 by K4. These are equivalent, right?
Those are not equivalent because we know the difference between the encryption of a key and the encryption of a data element.
No, so there's I changed my
Oh.
mind, so just one. So here you have K1 encrypted by K2, K1, and here you have K3 encrypted by K2, encrypted by K1. Are these equivalent or?
Yes, yes.
They are equivalent. So, and what will be the, so when you write for this basic lemma, can you show us the first?
Can I show us the, well, all right.
The first one, interpretation of code.
so I see. So R of E here. All right, so what's the problem here? Because R of the first expression is K1, R of the second expression is K3.
We can take it off.
Yeah, I'll have to think about that. Yeah. All right, well, so from this basic lemma, let me just say that we can prove something like this. That basically applying one step of the key recovery operator and then taking the pattern is going to give us indistinguishable interpretations, and then you just do that inductively, and you get that starting from any expression. And so any expression is indistinguishable from its pattern, and so any two expressions with the same pattern are going to be indistinguishable. Okay, so I want to now shift gears, because what we've been doing is thinking about how we could change the symbolic setting to allow us to get a soundness theorem even when we have a situation with key cycles. And another thing we could do instead of trying to change the symbolic setting is to go to the computational setting and to say, well, might it be possible to get encryption functions which allow us to do some kind of circular encryption? So this is a very expanding field called KDM security. KDM means key-dependent messaging. And so we're going to consider situations where not only do we have key cycles, but we have settings where we're allowed to do encryptions of arbitrary functions of secret keys under public keys. So we'll be working in a public key setting. And so basically, we can define security in this setting as follows. So we think of having a game with an adversary where the adversary is in one of two worlds. So the adversary knows a collection of public keys, but the adversary doesn't know the corresponding secret keys. Now, the adversary is going to have access to an oracle. And so the queries have the form an index I and then some function g. Now the function in different settings, or we may allow different classes of functions. The most general setting would be that g would be any polytime function. So our goal would be to have this to work in the setting where g is any polynomial time function. And in world 1, when we do a query like this, what do we get? We get the encryption under the ith public key of the function g applied to all of the secret keys. And in world 2, when the adversary does a query like this, what's returned is the encryption under the ith public key of some arbitrary string of the correct length. So we could just say, well, let's take the length of g applied to the secret keys, take a string of zeros of that length, encrypt that, and give it back. And so, of course, we're going to need some restrictions on g so that the length of g is always the same no matter what our inputs are. And so we're going to say that we have KDM security with respect to g if the adversary can't do better than guessing, much better than guessing which of the two worlds we're in. Okay, so this notion was proposed by Black, Rogaway, and Shrimpton, and they were doing it in the setting of computational soundness. And they were able to prove that you could get this kind of KDM security for polytime functions, but they didn't do it in a what's called a plain setting in cryptography. So in what's called the random oracle model, which is a setting that's widely used in cryptography, but there's some issues about how realistic it is. The idea is that you think that everybody, or you have a model where everybody has access to a random oracle, and then you say, well, then in the real world we can instantiate that random oracle by a secure hash function. And so in the random oracle model, they did get KDM security.
But totally this would not work for any of the standard, I don't know, RSA-based.
No, yeah, certainly it doesn't work, although.
And your G to make sure that the encryption according to K1 spits out the secret key.
Yeah, of course, yeah. So yeah. So just in the case of circular security, So we saw already that plain CPA security doesn't imply what's called one circular security. Yeah.
I'm saying even before circular. I mean, this definition would not hold. I mean, the distinguishability of world 1, world 2 would not hold for all polytime functions if we pick a public key system like RSA or the probabilistic encryption version of RSA. Just one point.
Sure, sure, yeah, yeah. I mean, well, I mean, in particular, I mean, if you have the G could just be the first projection or the ith projection, right? So you.
That's not enough because it will be.
I mean, we'd already lose security with an ordinary encryption system just by letting G be the ith projection, right? Because if we encrypt the secret key under the corresponding public key, then using the idea that we used before, we would lose security.
We use it, or we don't know how to prove that it's secure.
Well, no. We know that in the one circular case, I gave an example that shows that you have a encryption function which is secure when you encrypt messages, but it's totally unsecure when you encrypt a key under itself. Now, the question for longer key cycles is kind of open. So so just recently, there's some results. So using some new techniques related to indistinguishability obfuscation, they can show something like CPA security does not imply K-circular security. So what this means is that they can construct an encryption function which is CPA secure, but which is not K-circular secure. Of course, this doesn't answer the question of whether or not, under the assumption that some CPA secure encryption exists, does K-circular security exist? So could we somehow take a CPA secure encryption system without any other assumptions and use that to build a K-circular secure encryption scheme? Oh, K-circular would mean that, you know, if you have a key, if you have key cycles of length K. Yeah, yeah. So recently with my student and another colleague at UVic, we seem to have some partial results in this direction. So they're kind of generic assumptions, just saying that if you have a CPA secure scheme where you can do multiple encryptions reusing with respect to one random string. So typically when we think of encryption functions, they're randomized, but in every application, you choose some new randomness. So if we have CPA security in the situation where we can do multiple encryptions reusing randomness, we're able to, from that, get a circular secure encryption scheme. So I guess this it's not really done yet. So
Isn't the ability to use random strings in encryption sort of like circular already? Or is it secure to do this? I mean, would
are there CPAs? Yeah, I mean, many, I mean, sort of schemes that we know are secure, like Elgamal, or they're secure with this kind of randomness reusing.
So you have this kind of system under, say, PDH or?
Oh, yeah, okay, well, that's what I was going to get to. So, so sort of the breakthrough result in this area was this result of Benet, Halevi, Homburg, and Ostrovsky from 2008, where they get a construction of a KDM secure encryption system with respect to a class of affine functions. So they're doing encryption over a group, so you have a notion of affine functions over the group. So with respect to affine functions, based on the decisional Diffie-Hellman, they're able to get a KDM secure system. And with this class of functions, of course, that includes things like projection functions, and so we're getting circular security and clique security even, where all keys are encrypted under other keys. And so I don't really have time to describe the system to you. I'll try to give a toy example of something which is related, and sort of gives you the idea of how their approach works, and most of the approaches that came after them work. So I mean, this is just an example, but it's not my own, so I'll just point out that it appeared in a paper by by those authors. So first of all, let me just recall how Elgamal encryption works. Okay, so we need to start off with a group. The group is going to have prime order, and we're going to let G be a random generator of the group. Is the group? Yeah, it's cyclic. Yeah, it's generated by G. So those the group and the generator of the group are known publicly. So first of all, to generate our keys, the secret key is just a random element of the integers mod q. Sorry? Oh, yes, and the public key is the generator raised to the power of the public key. So the intuition behind this roughly is that it should be hard to recover the secret key from the public key because that's the discrete log problem. Now, it's not enough just to assume the discrete log problem is hard to prove the security of El-Gamal, but I'll get to that in a bit. Let me describe how encryption and decryption work.
So S is the same as SK.
Ah, yes. So to do encryption, what we first need to do is to pick a random value. So this encryption function is randomized. And our ciphertext corresponding to M is what we get by raising G to the power of R. And then, and taking the public key raised to the power of R and multiplying it by M. And then decryption. Well, the way this works is that we compute C2 times C1 to the negative power of negative S, and then we just do the corresponding calculations inside the group, and we see that we get what? Right? H is G to the S. And so we raise that to the power of R. We get G to the SR. Raising G to the R to the power of negative S, we get G to the negative RS. They cancel out, and we get back M. All right. So for El-Gamal to prove its security in the sense that we couldn't distinguish an adversary, again, could be in two worlds. In one world, they're able to get an encryption of a message, and in the other world, they just get the encryption of a fixed string or a fixed value from the group, and they can't distinguish between those two worlds. That's what it means for this encryption, an encryption system like this to be secure. And the security rests on something that's called the decisional Diffie-Hellman assumption. And decisional Diffie-Hellman says that the following two distributions are computationally indistinguishable. So in the first case, well, we pick two random values, x and y, and then we form this tuple where we get the last element by multiplying x by y mod q. Well, no, it doesn't really matter. We just multiply x by y, raise g to that power. And in the other setting, the fourth component of the tuple is just another random group element, and the DDH assumption says that we can't distinguish between these two worlds. So of course, DDH implies that discrete log is hard, because if we could do the discrete log, we would just be able to see what x is, see what y is, multiply them together, and see if that's equal to z, right? So the idea is that, I mean, just like, let's stick with intuition. The idea is that if we had DDH, then when we form something like a message times h to the r, that's like the message times g to the rs. And essentially, that just looks like the message multiplied by a random group element. And so essentially, we can think of ciphertext just like looking like random pairs of group elements. All right, so just have enough time, I hope, to show you a certain kind of KDM security for El Gamal. So we're just considering a very simple class of functions. Basically it's saying that for any a, we get a group element corresponding to a. We raise that to the power of s, and that's the function of s that we're allowed to compute, or we're allowed to see encryptions of that. And the idea here is that encryptions of messages of this sort can be simulated without knowing the secret key at all. Yeah. H to the, yes. So say we have a message which is f of s, then the corresponding ciphertext will be the generator to the r, and the other component will be m times h to the r. And now let's introduce this value t, which is r plus a, the a from the function that we're applying. Right, our ciphertext has the message m times the public key raised to the power of r. All right, so we just go, we simplify here. We get this g to the s times a plus r, which is g then to the s times t. And so, well, when we get to something like, oh, sorry. How do I want to say this? So basically, we're able to compute the encryption of f of s without knowing s, just by computing a tuple that looks like this. Now, the problem is that, OK, we've got this faked encryption of f of s. Maybe the adversary is going to look at it and say, well, OK, I can see that when I decrypt this thing, I get back f of s, but maybe this is not really an encryption of f of s. But then essentially, by the DDH assumption, really what the thing looks like is that it looks like just, it's going to have the same distribution as the encryption of a random ciphertext. And so not only is it possible for a simulated oracle to create these encryptions of the KDM function, they're encryptions that look good in the sense that they look like encryptions that could really occur by the encryption, real encryption of some message. OK, so for this result, it basically takes this idea, but can I say anything about it? It's going to use the idea of simulated encryptions again, but to get this for the whole class of affine functions, essentially you have to make messages be sequences of sequence of group elements, and then encryption comes down to matrix multiplication. And you get a kind of version of DDH based on matrices. So the security is based on a matrix version of decisional Diffie-Hellman. But I don't really think that I'm going to have time to talk about it. So you can always look at their paper or ask me about it if you want to. Thanks.